Okay, well, I guess good morning or good afternoon or good evening to you. It's morning here. I wasn't exactly sure what to present. I have too many slides, so I'll, please interrupt and ask questions, and I can skip through because some of it is from review talks, and you may be very familiar with some of this. So I just wanted to give some thoughts on plasma-based acceleration, and I'm going to concentrate on, underdense laser plasma or underdense beam plasma interactions and not deal with solid target or the very intense lasers where you might have QED effects. So I was not going to cover that. So I just want to list current group members and recent graduates from my group. And it's perhaps obvious, but the major driver for plasma-based acceleration remains the goal of reducing the size and cost of expensive, can you see this pointer when I do this? Okay, of expensive particle accelerators. So there are particle accelerators used to collide particles at the energy frontier. For example, right now the largest is the LHC, which is 30 kilometers of circumference. Or now another large machines are X-ray FELs, like the LCLS at SLAC, which is several kilometers long. So, these are 20 billion or more. This is several $1 billion to build a light source. So the question is, can you make it cheaper but still work? Because the critical thing is it has to work. So these leads to issues of efficiency, charge, beam quality are very important metrics. So it's not just enough to generate a few particles. You have to generate a useful number with a sufficient beam quality that you can do something with them. So to put things in perspective, for a energy EV range, in order to get high events, this what's called the luminosity must be very large, which is proportional to the number of particles squared and essentially the spot size squared. So these are things you want to make this big, and you want to make these very small. So when you work it out, you typically need nanocoulomb charge at 10 kilohertz, which means that you have a kilojoule per bunch that's being collided, or that's 20 megavolts of average power in the output beams. Assuming some efficiency, that means you need 200 or more megawatts of average power. So the wall plug efficiency of your driver becomes very important. You need high beam quality. So the energy spread of the beam has to be between 0.1 and 10%. And you need very low emittance such that you can focus the beams to very small spot sizes so that these are small to get this luminosity large, which means something called the normalized emittance, and I'll come back to that, needs to be less than a micron or a millimeter milliradian. And the whole idea is it has to be low cost compared to conventional accelerator options. So let's say a tenth of $10 billion per TeV, something on that order. And to reduce the cost, the assumption is you have to reduce the size. So the gradients must be greater than 100 MeV per meter. And you have to have an efficiency, total efficiency from the wall to these final bunches of a few percent. So if you wanted to make a compact X-ray FEL, the energy is not TeV, it's GeV or higher. And now it's the peak current that matters, and you want 10 kiloamps in the peak current. And the beam quality is actually more challenging. You need energy spreads of around 0.1% and emittances that are substantially less than a millimeter milliradian. So the question is, why would you consider plasmas? So conventional accelerators are limited by the peak power and breakdown to about 20 to 100 MeV per meter. So a plasma, because it's fully ionized, has no breakdown limit. So you could maybe get 10 to 100 GeV per meter gradients. And as I said, you want these gradients to be the gradient on a beam or a nanocoulomb or so of charge. So it's called the beam loaded gradient has to be 10 to 100 GeV per meter. So I'm assuming that at this workshop, you're all familiar that if you take a simple one-dimensional argument for how big the acceleration gradient can be in a plasma wave moving with a phase velocity at c, you go through Gauss's law, assume that the density perturbation in the wave is about 100%. So this is assuming still a linear wave, even though when this is very large, it's a nonlinear analysis. It turns out that you end up with an engineering formula that the electric field you can get in a plasma for a plasma wave with a phase velocity of c is on the order of 10 GeV per meter, and it goes as a square root of the density. So at 10 to the 16th particles per cubic centimeter, it is 10 GeV per meter. So then the question was, if I need large gradients, I need a plasma wave with a phase velocity near the speed of light. I hope that's clear to everyone because you're accelerating particles which are going to be moving near the speed of light. So for them to stay in phase for long periods to get large amounts of energy, then you need that. So you need fast boats to make these wakefields. So we'll come back to this. So the question is, what is a fast boat I can use in a plasma? And one of Predimann's mentors, John Dawson, essentially came up with in the late 70s and early 80s 2 ways to making these fast boats. One is a laser pulse in an underdense plasma. So the group velocity of light can be very close to the speed of light. It's a little less than the speed of light in a plasma. Or you can use a relativistic particle beam, an electron beam, for example. And in both cases, the laser pulse is a bullet optimally, which means that its pulse length is half a plasma period, and its spot size should be matched roughly to the plasma wavelength. And the particle beam as well needs to be very short compared to the wavelength. So you want it to be very short. So John Dawson proposed these ideas in a paper by Tajima and Dawson in 79, and then Pizan, Chen, Dawson et al. In 1985. So I've cut out here the abstracts of these papers. And I want to stress that this is a very humble beginning of a new subject. They were one-dimensional or very simple linear arguments. They relied on simulations that I could perform on this laptop in a fraction of a second. So for those who are doing particle and cell simulations now, they use only 5,000 particles for 500 time steps. So the point is that if you're creating a new effort, remember the required lasers and the required particle beams did not exist when these papers were written. And I'll come back to that, and it's kind of a lesson that doesn't mean you should stop performing basic research. Another thing about this field, although it's driven by these large projects of a linear collider or a light source, that the field of short pulse laser and beam plasma interactions is fundamental to this field, but it's also at the forefront of basic science. So I've just shown a sample of covers of high impact journals in which an article was mentioned, or for example, here and here and here, results from those papers actually show up on the covers and here. And this is important because it attracts very talented graduate students because it is such basic and fun research. Another thing to stress is that the progress of this field has been due to a close synergy between simulation and experiment. And so an example, I put covers where each of these articles contained experimental results, but where the interpretation was supported by simulations. And I think that if you're going to develop an effort, you need to also stress that you need experiment. Obviously, experiment is king, but you need to develop a close synergy between experiment, simulation, and theory. So if what I'm about to be talking through is very familiar to all of you, just let me know and I'll kind of skip through it. But I wanted to do a little review of some important concepts for plasma-based acceleration. So one is called the quasi-static approximation, which was developed by Sprengel, Ezeret, and Ting in 1990, although it does have some earlier, there are papers where some of the ideas were presented earlier, but they put it all together. So the idea is that for this field, because the wakefields and the drivers have velocities very close to the speed of light, that it makes sense to make a mathematical transformation from z, x, y, and t to c, which is z minus v phase t, x, y, and then s, which is z. So this represents where you are in the wakefield with respect to the head of the driver. And this variable here represents how far the driver has moved into the plasma. So that's what I say. These meaning of these variables are c is the distance from the front of the driver, and s is the distance the driver is propagated. And the mathematical meaning of the quasi-static approximation is the realization that the wakefield evolves much more slowly on a distance compared to the wavelength of the wake. So another way of saying that is that the driver can move many wake wavelengths into the plasma before its shape changes. And that is the crux of the quasi-static approximation. But what's important is to be thinking about these wake variables. Another is to recognize that the forces inside the wake on particles moving with a velocity very close to the speed of light depend on a single wake function. So if one looks at the electric field along the direction that the driver is propagating and looks at the force in the perpendicular direction on a particle with a velocity equal to c, so it's moving as well in the z direction with a velocity c. If one does this and assumes that the wake function only depends on z minus ct and x and y, after a couple lines of algebra, one can show that the longitudinal force and the transverse force are given by the longitudinal gradients and the transverse gradients of phi minus az, regardless of what gauge you end up choosing. So that means you want to think about a wake function or a pseudopotential psi, which is phi minus az. I've seen papers where they chose a gauge where phi was equal to az. If you do that, things become much more complicated. So if you don't, then the forces are simply gradients of psi along the beam propagation direction and perpendicular to it. So the quasi-static approximation, which uses these variables, as I said, was Sprengel and Ezeret, and then these ideas were implemented into PIC codes by Mori and Atkinson and my graduate student in a full 3D code. And I'll come back to that. So now if you look at the linear theory for particle beams and laser drivers, and let's look at where the wake fields are produced by either a laser or a particle beam. And let's first consider wide beams, which means the spot sizes are comparable or larger to the wavelength of the wake. Then there are no differences in a certain sense between how a laser or particle beam excites a wake. And you can write down a single equation, harmonic oscillator equation for the density perturbation, where it's driven by the beam driver, and the ponderomotive force related to A0 squared over 4, where A0 is the normalized vector potential. So the transverse profile of the wake, therefore, then follows the driver. There's no transverse derivatives here. So you can rewrite this in terms of the wake potential, psi, and that's what I've done here, because I told you that all the forces on a particle beam are in terms of psi. And the important thing to realize too is that in this regime, regardless of whether the particle beam is a positron or electron, this equation simply holds. You just replace the sign of the charge here. So the solution for the wake then is easily calculated via Green's functions. So here is what the wake function is. I use the Green's function, integrate over the charge density of the driver or of the ponderomotive potential. And this shows, using our simulations, the agreement between linear theory and our codes, and that you get this force by simply taking gradients of this pseudo-potential. Now, you can also do linear theory for an arbitrary transverse profile. It is still straightforward for both particle beams and a laser driver. And the wake potential in this case is now given as follows. And notice that for a laser pulse where the ponderomotive potential, the result is unchanged. But now for a particle beam, it's a little more complicated because you have this modified Bessel function, and you have to integrate along r and phi over the distribution of the beam, which you don't have to do when you have a laser pulse. This leads to a very important difference between the wake from a particle beam and a laser when it's very narrow. And that is that a very narrow, so this is a plot of the pseudo-potential versus radius. And the dashed line is the beam profile, which is very narrow compared to a skin depth. And the red curve is the wake potential, which still extends out to a skin depth. So therefore, a narrow particle beam does not make a narrow wake, while a narrow laser pulse would create a narrow wake. So there is no reason to use a very narrow laser. It's also very hard to guide, but it does make sense to use a narrow particle beam for reasons I'll discuss shortly. So I think an important thing to stress is if I go back and I use this linear theory and I say I want to make a large pseudo-potential, because I want to make a large wake. After all, that's the reason to use a plasma, is I can make wake fields that are big. Then I need a large normalized vector potential, excuse me, or I need a large normalized beam density. I also need the pulse length to be matched to the plasma frequency, and the spot size to be on the order of half of the wake's wavelength. If I just use those requirements, then the laser power must be 100 terawatts. And the particle beam current must be tens of kiloamps. And I point this out because lasers of this type and particle beams of this type were really only available in the last 5 to 10 years. But that did not stop Tajima and Dawson and Chen and Dawson at all from writing papers in which they talked about making a wakefield accelerator. And if one had waited to work on the theory and the simulations until these lasers were ready, we would never be in a position to have done anything. So I stress 100 terawatt, 50 femtosecond lasers and 10 kiloamp GeV particle beams were more than 25 years away from when Tajima and Dawson were published. So the lesson, even of a new idea, is based on 1D theory and simulations. You still need to push forward. So I'd like to discuss something for a fixed amount of charge. So if I have a kiloamp, 10 kiloamps of current, you can always make the beam density to the plasma density very large by decreasing the spot size of the beam. All right, so it means that it's not just N beam over N0, which is important, but what matters is what I call the normalized charge per unit length. So N beam over N0 times Kp squared over sigma r squared. So essentially, what is the beam density if you spread the charge out to a skin depth size? That's what this parameter means, okay? Which works out to be the current over 24 kiloamps. So if you want to make very large wake fields with a particle beam, and you want to make it very narrow, then n beam over n zero is going to have to be large. So one thing we worked on about 5 years ago was to show that linear theory will still work for particle beams, even when n beam over n zero is less than 10, as long as this normalized charge per unit length is less than 1. For positron beams, it required n beam over n zero to be less than 1. Now you might be asking, maybe even though you're interested in developing a program in laser acceleration, why you would worry that much about particle beam theory. The point is that no matter how you create the wake, you need to load particle beams into the wake. So you need to understand how particle beams modify the plasma as well. And so a lot of what I'm talking about was driven by the need for understanding what's called beam loading. But in any case, you also can create wakes using these particle beams. And so what matters is this parameter being large compared to 1 or being 1-ish. So here's an example of what happens to the character of the wake when the ponderomotive potential, I'm sorry, I converted a keynote to PowerPoint. So you can see this. This is the ponderomotive potential or this normalized charge per unit length. These are the parameters which tell us how big the wake field will be for a laser or a particle beam driver. So here I've shown simulations where I've taken a particle beam driver where Kp sigma r is 2.8, which an n beam over n0 was less than 1. So the particle beam moves through and it makes a linear looking wake. So over here is a line out of the electric field. Here's where the particle beam driver is, it's moving this way, and it creates a very nice sinusoidal wake. Now for the same amount of charge, all I do is I reduce the spot size. So if you remember, that means that the n beam over n0 has gone from some number to 2.8 squared bigger. So now it's bigger than 1. So now as this particle beam goes through, it's narrow enough that it actually doesn't just push particles forward and backward, it pushes them out sideways, and you create a nonlinear wake. So now if I look at the wake field, it is no longer sinusoidal. Now I can go to the extreme limit, where Kp sigma r is much, much less than 1. So here's the particle beam, it's moving this way. It now blows out all of the plasma electrons, creating this region of no electrons. And now it makes a very nonlinear looking electric field wake field. And it looks very similar to what, if you're looking at nonlinear wakes created by a laser pulse. So this, instead of a particle beam was a laser pulse, and the pseudo potential here for the laser or the normalized vector potential was much bigger than 1, you create a similar looking wake. Are there any questions? Okay. So now that leads to this idea of nonlinear 3D wakes. And they were discovered in the early 1990s, first by accident by Rosenzweig and Hall, who were looking at what happened when they used very narrow particle beams. We then at UCLA said, okay, well, instead of using a a particle beam, let's use a laser. Pukov and Meyerteveen in 2002 considered 500 terawatt lasers and looked at an extremely nonlinear regime of this. That's now referred to as the bubble regime. And then my graduate student looked at this for laser pulses in a kind of a nonlinear but not extremely nonlinear regime, as was considered by Pukov and Meyerteveen. So the point is, as I've shown here, that whether you use a particle beam or you use a laser pulse, as long as the parameter of the ponderomotive potential or the normalized charge per unit length are bigger than 1, you make these very nonlinear looking wakes, where the space charge force or the ponderomotive force pushes the plasma electrons forward and to the side, such they form this very well-defined sheet, which then is pulled back by the ions, they overshoot, and there are other wavelengths behind. The whole idea is that you would load the wake with an electron or positron beam somewhere, which would then get accelerated along with the beam, and you would take away energy so that nothing is left behind. Okay, now you need a nonlinear description to describe these wakes. So really all successful laser wake field experiments to date have operated in a regime of a nonlinear wake, and the same for particle beams. Okay, these are very ideal for accelerating electrons, but not positrons. They're very stable. And I want to point out there are similarities, but there are differences between the structure of these nonlinear wakes created by particle beams and lasers. You know, these are things that can be discussed. So the field structure in the nonlinear blowout regime is best described by the pseudo-wake potential. So the pseudo-wake potential not only describes how a relativistic electron behaves in it, it also is useful for trying to explain how this wake is formed. Or in particular, we realized you want to describe the dynamics of electrons inside of this sheath. Okay. So if you look at the field equations in the Lorentz gauge for the A and phi, you then make the quasi-static approximation, which is that d by ds is much smaller than d by dc. These two equations end up becoming transverse Poisson-like equations. If you subtract these, you end up with an equation for the pseudopotential, which is simply a Poisson-like equation where the source term is not just the charge density, it's the charge density minus jz over c. Then once you have an equation for this, you can get what the acceleration fields are, and you can show that in this blowout regime, this force can be obtained using Gauss's law, where it's just simply from the ion, the leftover ion charge. If you use those field equations, you can get an equation for what the blowout radius or what the electrons in the sheath are doing. And I don't have time to go through the details, just suffice it to say, you can get such an equation using a phenomenological theory, and therefore have a predictive theory for what the wake structure will be like. The pseudopotential in the very nonlinear regime can be written in this form, where you've got the blowout radius squared here as a function of c. The electric field, therefore, if you differentiate this, in this limit is 1/2 c. So it has a linear slope, which is just like a one-dimensional nonlinear electric field. But for those of you, and I know Preionized worked on this many years ago as well, but it's for different reasons. And you can work out that the maximum electric field is, because it has a linear slope, I just need to know what the maximum blowout radius is. Then you can get what the field is in terms of the square root of c, or the square root of the normalized ponderomotive potential. I know this is a lot to cover, but I think it's important to point out that inside of this structure, what is very important is that the accelerating field across the transverse direction is flat, which means that if you load a particle beam in here, they all feel the same accelerating field. Therefore, the energy spread can be controlled. In addition, the focusing force is linear, and I'll come back to why that's important in a second, but that affects the transverse dynamics of the particle beam, which affects how the emittance of the beam will evolve. Okay, so I'm going to just skip this. It's a kind of an extra slide just saying what I said, which is that in the nonlinear wake fields is ideal for accelerating and focusing electrons, not for positrons. I'll come back to that. And the trailing beam does not modify the wake, these properties, ideal properties of the wake potential, all right? So there's something called the Panofsky-Wenzel theorem. If people aren't familiar, I can go through it, but essentially is a relationship between the longitudinal gradient of the transverse force and the perpendicular gradient from the accelerating field. And these come from the fact that both forces come from a single potential. And in any case, these wakes have ideal properties for accelerating trailing beams. All right, so now let's go to the transverse dynamics and the beam quality. There's something called the emittance, which is basically the area in transverse phase space. So if the beam's propagating in Z, then the two transverse directions are X and Y. So let's look at the phase space in the X direction. So you have spot size in the X and a maximum px. So if this beam propagates in vacuum, then this spot size will evolve by this formula, and the kind of diffraction distance is given by what's called beta star, which is the spot size squared over the normalized or over the emittance times gamma. So the geometrical emittance, which is the normalized emittance over gamma, plays completely analogous role as the wavelength does for a laser. So you can think about this as the analogy for a particle beam to the Rayleigh or diffraction length. All right. So what you have is the particle beam inside the plasma is trying to expand due to its actual diffraction, but inside the plasma, the single particle oscillates according to this wake function. All right. So if the focusing force is linear, I didn't mean linear meaning small, linear meaning it's proportional to the distance you are away from the axis, then in a particular transverse plane, it obeys a simple harmonic oscillator equation, which says that no matter what your radius is, these particles are going to rotate around together at the same frequency, and the beam will rotate together if the focusing force is linear. Now, I don't know whether it's obvious, but it's sort of not discussed why linear forces are really important are that for a linear focusing force, the motion in the two transverse planes are independent of each other, all right? So the real focusing force is proportional to R, so you can show that that means that the focusing force in the X and Y directions are not coupled to each other. All right, so let's come back to a little bit more. So now let's consider a focusing force that may not be linear. So here you have the transverse phase space, and the particles are going to be rotating.
Hello, we can't hear you.
Hello?
Yes, now we can hear.
Can you hear me?
Yes, yes, now.
Yeah, okay. So what happened? Okay. All right. All right, so now what happens is that the particles with larger x, if the focusing force is not linear and the focusing force becomes smaller, will rotate with a smaller frequency than particles near the axis. So therefore, as this thing rotates, particles on the edge will be left behind. As you rotate further, they start to stretch out even more. And after many betatron periods, which is the frequency that they rotate, even though the original phase space volume was this, and phase space area, looks still conserved, effectively this whole circle becomes filled in with this complicated structure. So therefore, nonlinear focusing forces can lead to the emittance growing, which is very, very bad. All right. So the way you get around that is you have to match the diffraction length to the effective focusing length, which is the frequency divided by the speed of light. If you match that, then you can get a beam whose essential emittance won't grow much. So for linear focusing forces, a Gaussian beam remains Gaussian when matched. For a nonlinear focusing force, if you use a matched beam, you can still limit emittance growth. It's just that the transverse distribution of the beam is not Gaussian anymore. But as I stressed, it needs to be linear because you do not want the two planes to couple to each other, because that will lead to emittance growth. So really, it is very advantageous to have focusing forces which only depend on R, even when they are nonlinear. So if you wanted to, you are now ready to think about beam loading if you follow all these concepts. So it is not just enough to accelerate a few particles to a TeV or to 10 GeV. It's very important that you understand what happens when you load a lot of charge into these wakefields. So beam loading is a study of how to place the bunch charge to extract energy with high efficiency while keeping the energy spread small and keeping the emittance preserved. Okay? So this involves understanding how much charge can be loaded, where to place the charge, and how to shape the charge. And I stress that when you go through all of this, you do not want the accelerating field to depend on where you are in the wake, and you do not want the accelerating field to vary across the beam. So that means you'll have very little energy spread. You also want the focusing forces to be linear to limit emittance preservation, and you don't want the focusing force to depend upon where you are along the beam, because that would require different matching spot sizes along the beam. So I can give these slides later so people can read through this, because I know this may be a lot to digest if you're not familiar with it already. So the details of linear and nonlinear beam loading are in the literature, and I can be more than happy to discuss with people in private conversations at another time.
Yeah, sure, we'll welcome that.
Okay. Now, so the point is, in these nonlinear wakes, which are very useful for accelerating electron beams, whether that is for a linear collider or for a light source, it's nonlinear. So although you can develop phenomenological theory, and there's a lot of predictive theory you can try and develop, you still require fully nonlinear simulation tools. And the particle and cell method has been shown to be really the tool of choice and been the most useful. So I'm assuming you're somewhat familiar with the particle and cell code, but the idea is as follows. You take particles and you have positions and momentum. You use these to deposit them onto a grid. So these particles have continuous variables, but you deposit the current and the charge density at discrete grid points. You use those to solve Maxwell's equations, which are been discretized, to get electric and magnetic fields. You use these to get the forces, and you interpolate them back from the grid to the particle positions. You use these to push the particles discretely in time to new position and new momentum, and you repeat the cycle the desired number of time steps. And the CPU time is dominated by the particle pushing, and today's codes are on the order of 100 nanoseconds per particle step. And not all PIC codes are the same, and I think that's a very important message. So I'm going to go through this a little quickly, but I wanted to give you a state of where we were in 1990. So in 1990, we realized that the propagation length of the laser or particle beam was going to be much, much bigger than the pulse length. So that meant, if I look at this picture, you have a laser or particle beam here moving from left to right. As it does, it generates this wake field, which has a group velocity of 0, so it's left behind the laser pulse of the particle beam. Ideally, you want to put your particle beam that you want to be accelerated behind it, which would absorb all of this energy. So I really don't care what this wake is doing way, way behind here. All I want to follow is this box near the laser pulse or the particle beam driver and a few wavelengths. Okay, so here's the same thing where I use a particle beam. So I only need to follow this window. So inside of this window, in a real plasma of 10 to the 16th density or so, or higher, there's only 10 to the 12th to 10 to the 14th particles. And the number of real electrons in this beam was 10 to the 9th to 10 to the 10th. And we realized even back then that computers were going to evolve and that someday I could actually model and follow this number of electrons in the beam, this number of electrons in the plasma for 100 thousands or so time steps. You don't necessarily need to follow every particle, but it just meant that these one-to-one or full-scale modeling of experiments was going to be possible if we developed a moving window. So this is just to show if you got time steps versus number of grids, that rather than following the grid steps, this whole blue, you just use this moving window, and the sort of area in ZT you need to follow is much narrower and it's much more computationally efficient. And I want to point out, if there's a person, JJ Su, who was a graduate student around when I was, and he deserves, although we implemented a lot of this, he deserves much of the intellectual idea for this. Around that time, we also realized that parallel computing was beginning to take off in the early 1990s. This is a plot of system performance in megaflops per second and year, and following a Moore's law. And as you go up here, new technologies and computer architecture keeps being evolved. But we're still marching towards exascale computing. But we realized in the 1990s that we were going to be marching along this parallel computing path. So what we did was we wrote a proposal to the US High Performance Computing Program, to NSF. We called it Full-Scale Numerical Experiment to Test a Future Plasma-Based Accelerator. In this proposal, when Tera was the prefix of the day, not Exa, we proposed to write a 3D parallelized PIC code, implement a moving window, to use what is now everyone refers to as a boosted frame, and to study PWFA and LWFA and what now people refer to as the bubble regime. We did propose this in 1992, and I want to give it as a lesson to the young people in the audience. This was not funded. So if you write a proposal and you think it's good and it's not funded, you still try and figure out a way to implement your ideas. So we did not give up. We started to write parallel PIC codes with moving windows. We tried boosted frames. I don't have time to talk about this. It could be another talk, or people can talk to me about it. All of this effort, starting in the early 1990s, evolved to what is called OSIRIS 4.0, which is our major PIC code, and to quasi-static PIC codes, which I will come to that. Okay. So OSIRIS 4.0, which has evolved from OSIRIS 1.0, which was written by my graduate student in the late 1990s, is now a collaboration between IST in Lisbon and UCLA. And Ricardo Fonseca deserves tremendous credit and leadership in many respects of this effort. If you're interested in maybe getting access to it, send me an email and we can talk about it. But it is a massively parallel framework. It is scaled to more than 1 million cores. It has the ability to run on Intel Phi and GPU. It has dynamic load balancing. It has a QED module that I won't have time to talk about. Particle splitting and merging algorithms, a quasi 3D algorithm. It has the capability to run in a boosted frame. It's got a Coulomb collision module. And there's a lot of people at IST and UCLA developing it, so it continues to be developed. Now, another thing that was worked on was the recognition that reduced models, or exploiting the quasi-static approximation, could be a very useful thing for modeling plasma-based acceleration. So if you look at this window, once now we have a driver, it's a beam driver, but it could be a laser as well. And as long as the shape of this driver does not change, then even if it moves from here to here, the wake behind it just moves along with it. But all you do is you shift it, but its amplitude and phase and everything does not change if the beam driver's shape does not change. So the realization was that you then calculate the wake, and then you take a very big step forward for the beam from here to here, where its shape has changed, and then you recalculate the wake. So I don't have to take little time steps forward. I can take a big time step forward. I just have to ensure that I resolve the evolution of this beam. If I do that, then I have an algorithm which is much more computationally efficient. There's a way to combine this for a laser where the laser, you average over the high frequency and you use what we call the ponderomotive guiding center concept. And you can also then implement this algorithm for laser drivers. And credit, I should say, for taking this quasi-static approximation and putting it into a PIC code really goes to Moore and Atkinson in 1997. Dan Gordon was the one who put the ponderomotive guiding center into standard PIC codes. It came from their work on quasi-static codes. And then my grad student wrote a 3D this is a 2D quasi-static code. And my grad student wrote a 3D quasi-static code. And this code, as I'll come back to it, is now open source. Well, here we are here. So now you have a 3D quasi-static PIC code called QuickPIC. It is scaled to over 100,000 cores. It requires a predictor corrector routine, so it has similarities with a Darwin code, so it's more complicated than a standard PIC code. And this movie here illustrates how it works. But as I told you, there's a version that's open source, and if you want to get a copy of it, let me know. We can help you do it. But you just go to this website. Okay, so it embeds a 2D PIC code inside a 3D PIC code. So you load a bunch of plasma particles in front. They then are pushed back through the beam. Once they've moved through the beam, you calculate what the forces are in the wake field that cause the laser or particle beam driver to evolve, and then you push it forward a big 3D step and you repeat the process. So here you can see the particles moving back through the beam. They're pushed out. A wake in the blowout regime is formed. After at the back, you use the forces. You push the particle beam forward and the shape changes, and then you redo the calculation. So this can be 100 to 1,000 times faster, and we benchmarked it with no loss in accuracy for appropriate problems. Okay, so these codes scale to 1 million cores, or 100,000 to 1 million cores. Therefore, you can, and I don't know what access to computers you have right now in India, but you know, if these codes will scale, and it really enables you to do very large problems if they are required. Sometimes it's not required. There's a lot you can do on smaller systems, but if you are required to do a very big problem, these codes will scale. Okay, so what is currently being studied in plasma-based accelerator research? And it's generating self-consistent beam loading scenarios of a single stage with particle beam or laser beam drivers for both electrons and positrons, staging and the manipulation or manipulating the 6-dimensional phase space of self-injected electron beams. So let me go through a few of these. If I'm running out of time, just let me know and I can skip to the conclusion. All right. So what is the goal? The goal is a linear collider. Whether it's by particle beams or laser beams, the current concepts require staging 25 or 50 stages for electrons and for positrons, where within each stage, you're going to gain about 25 GeV for this witness bunch. Here, there's a drive bunch that has to be different drive bunches go into each of these stages, and they have to be synchronized so that this witness bunch can gain 25 GeV, be staged, transported back to this one without its emittance or its energy spread changing, and without it going unstable. It's a big challenge. So this is the ultimate goal for a linear collider application, whether it's a laser beam or particle beam driver. So one beam loading option is a nonlinear beam loading option, and this only works for electron bunches. So here's a dry bunch, a laser particle beam creates a wake. We've created an analysis of what this blowout radius does. When you load particle beams into it, it changes the trajectory, and that's essentially how beam loading works. We've figured out how to shape the bunch such that the accelerating field remains flat inside. And this is a cartoon where you have the dry beam and a trailing beam. We've shaped them such that the dry beam slows down together, the accelerating beam slows down, and this leads to very, very high efficiency. 50% energy transfer from the dry beam to the trailing beam is possible in this beam loading scenario. So this is just another illustration where we didn't use shape, we used Gaussian bunches, and we still got around 48% energy transfer efficiency. So there's a dry beam, here's a trailing beam. What is interesting is you can see that this beam is starting to hose, which for those of you in plasma physics, this is really related to a streaming, what are in plasma physics we call streaming instabilities. And it's something we have to figure out how to mitigate. So I'm skipping through a little bit because I know I'm, okay. So here's a movie where we have a dry beam and a trailing beam where this starts at 25 GeV, this one starts at 25 GeV. This is now a stage where this is still 25 GeV, but the trailing beam was a 475 GeV. And this just shows, that we can get this trailing beam to be accelerated reasonably stably with very, very high efficiency. And it's gaining 25 GeV in just 1 meter. So we're getting 25 GeV per meter gradient. So let me just show it. You can see this is because the beam is not matched. So you can see the spot size oscillating due to these betatron oscillations. That's why you can see this expanding, because at higher energies, it's not nearly matched. Anyway, so this is a self-consistent simulation with all the nonlinearities showing very high energy transfer efficiency. But this is a point, I'm not sure how familiar everyone is there, but matched beams lead to ion collapse. So let's see what I mean by that. If you look at a trailing beam, the beam density is the number of particles divided by the spot size squared and the pulse length. I need about 10 to the 10th particles for a collider application. I need the spot size matched so I don't have emittance growth. And that's determined by the focusing force inside of the channel and the emittance. So if you work it out, that for collider applications, the beam density, the plasma density, is 10 to the 4 to 10 to the 5, which means that the ions will be pulled inward during the transit time of the bunch, and that affects the focusing forces and can lead to emittance growth. And people were very concerned about this. So to put it in context, it required us to use simulations which are 2,000 by 16,000 by 16,000 cells. Even that wasn't enough because the matched spot size of this trailing beam is 1,000 times smaller than the radius. So what we then did simulations where we zeroed in on here. And this is a cartoon of that. So this is, we blow up this region and we only simulate near where the beam is. So this here illustrates, this is the ion density. So the ions have been pulled inward and this affects the focusing forces. All right. So the main thing is when we simulate this and we use spot sizes which are asymmetric, which is what you need for a collider. And I can explain later if people are curious and they're not familiar with why you do that. that the emittance growth is actually much less than expected. So here we have the emittance growth in a plane in which the emittance was 2 millimeter milliradians. Here it's 0.4 millimeter milliradians. And you can see that the emittance growth, even in these two planes, is actually not that bad. And once the beam finds its nonlinear match spot size, the emittance growth does not grow anymore. So we believe now that the emittance growth due to ion motion is not the issue that people had thought it was, which means that our beam loading scenario is something to be seriously studied. All right, so let me switch gears and finish up with sort of a grand challenge research problem, and this is related to laser wakefield acceleration, is the generation of ultra-low emittance beams and the manipulation of 6-dimensional phase space. So the laser wakefield in the blowout regime, remember, you got a laser pulse, it creates this wake. Some people call it the bubble regime. I think it's a little different than that in the sense that the bubble regime was where there's so much self-loaded charge and it's in a very nonlinear regime that the way a wake evolves is very different. But for the purposes of this, you consider them the same. You have a bubble in the blowout regime where you now have this evacuated region with this ion focusing force, and you want to figure out a way to get electrons in here to be accelerated. So self-injection and the generation of how to accelerate these unique high-quality beams is really the active area of research at the moment. So I'm going to skip through this. If people have questions about it, basically we have followed an idea by Lifshitz, and my grad student implemented it and used a new charge-conserving current deposit, so improved on the idea significantly. And the idea is that you can't use an azimuthally symmetric code to study lasers because those are radially polarized lasers. So if instead you expand the fields in azimuthal harmonics, you only need one azimuthal harmonic to describe a linearly polarized laser beam. So if you truncate the expansion, you can write a PIC code for studying lasers that their spot size remains azimuthally symmetric. And there are a lot of problems that you can do large parameter scans for this, and we have implemented this, and it is part of OSIRIS. And we benchmarked it, and the agreement is very, very good. So a message here is that code development continues, new ideas come about, and we continue to implement and improve them into OSIRIS. All right, so let's look at ionization injection into a laser wakefield or plasma wakefield acceleration. So this is a picture of a laser pulse moving from left to right. This is the electric field that is created, okay? And Preionized, I don't know if he remembers that there's a paper he wrote with Kohlsrud in which he talked about what happens if you ionize an atom inside of a intense laser pulse, that electron then can gain significant energy because it's not limited by the conservation of canonical momentum, bringing it back to rest. So there's a similar idea here that if, in order for a particle to be trapped, the difference in potential from where it started, which would be in front of the laser, has to be compared to where it ends up in the back, has to be sufficiently large, which can be very difficult to achieve. However, if you excite or ionize an electron, create it inside the wake, where the potential is large, basically here, then it's much easier to trap and easier to control. So the idea of ionizing atoms inside of the wake field to trap particles is now an active area of research. It evolved from Chen et al. In 2006 to Oz, Pack, et cetera. And the idea has really been improved a lot to generate very low emittance beams. So an active area of research is ionization injection of particles into the wake. This leads to another interesting idea that we recently published, was that because the ionization occurs at peaks of the laser amplitude, then they will be created in spacings related to half the laser wavelength. It will be created where the laser is intense. These particles then move back, and this spacing shows up where they get bunched actually at even a shorter wavelength, but they remain nano-bunched at back of the wake where they're trapped. And we've shown that they are trapped at spacing which is 1/3, something on the order of 1/3 of the laser wavelength. So this is a plot of the transverse momentum or the axial momentum versus Z, and you can see that these electrons are actually bunched, which is a very interesting thing that is now being explored. So there's just a lot of new ideas coming about, and there's a lot of work left to do, a lot of new ideas to explore. Another is what we call down ramp injection. So when the laser or particle beam moves down the density gradient, the wavelength of the wake expands, but the driver is moving forward. So therefore, the phase velocity at the speed of light. So therefore, this point moves backwards with respect to something moving at the speed of light. So this point is slowing down, which makes it easier to trap particles because you're making the phase velocity substantially lower. So we have shown that this down ramp injection process in the blowout regime actually unexpectedly leads to incredibly low emittance beams on its own. And we're showing that you can make with laser beams as well brightnesses that are much, much higher than in any conventional photocathode. So this is pointing directions for making compact XFELs based on plasma-based acceleration. All right, so let me wind up. We at UCLA have a particle and cell and kinetic simulation software center. It's funded by NSF. Some of our codes are available, they're open source. Others can be obtained through an MOU. If you're interested in learning about them and visiting UCLA, please let me know. They are now, the access is international. You can see there are places using OSIRIS and QuickPIC all throughout the world. I'd be excited if we had more dots here in India. This slide did not transmit way. I just want to point out, and I could talk about it later, that we're thinking about how to reduce 10 million core hour ROM.
Hello, we can't hear you.
So that we can you hear me now?
Yes.
Hello?
Yes, now I can hear you.
Hello? Okay. So we're working on ways to reduce the turnaround time for these large simulations down to a few seconds so you can guide experiments. I'd say over 5 years, maybe there's a path to such a thing. So let me just conclude. I know I've gone over and it's late, so thanks for listening. That, you know, the field is still, even though it's been in existence for a while, it's still incredibly exciting and vibrant. And that not only does it have these large sort of projects for goals, which would be a linear collider or a compact light source, the field of intense and short pulse laser plasma interactions is rich in basic and exciting physics. It's leading now the use of simulations in this field is accelerating the rate of discovery. So it's a lot of the physics is nonlinear, so it requires the use of fully nonlinear codes. Real-time feedback of experiments and tuning designs are on the horizon. We now realize, and we're working on the need to generate and manipulate the 6D phase space of low emittance energy spread particle beams. Start to end simulations of compact FELs is on the horizon. And I really believe that if the investment was made in an experimental program anywhere, that one could potentially make a compact XFEL in a 10-year horizon. And we now understand a lot of the key physics and a path towards asking and designing a linear collider based on plasma concepts. And so we've got a laundry list of things we need to study, but we have that list, and which I think is a very important milestone. And the next 10 years will be very exciting. So thank you for your attention, and I'm sorry for going too long.
Thank you very much, Warren, for that excellent introduction to the subject. I will see if there are any questions. Any questions?
Hi. The talk was very exciting, and like you talk about, like if anybody wants to know, like learn the software, then how to do that, like to contact you or what?
Yeah, so I think what we'd like to have over the next period are some workshops on how to use some of the tools. So I would say that QuickPIC is open source. So if you go to the website, you can find a path towards getting access to the code QuickPIC. And then once you do that and you have questions, let us know. And based on that, we can decide the best way to do things. If there's enough people, then we could figure out a way to help some of the travel expenses for people to visit. I could talk to Preionized about how to do that. With OSIRIS, the access is through an MOU, and I would talk to Preionized or others who would be in charge of controlling how that is handled, and then would have a list of the people who would want to use it. So the answer is that one is open source, the other is you can get access through an MOU that is not that restrictive. And by MOU, I mean a memorandum of understanding. It's just this fancy name where we kind of agree on how it would be used. So I think that contact me, but I'm going to be talking, I think, to Preionized tomorrow morning, and that's one thing I could talk to him about.
Okay. Thank you.
Any other question? I'd like to ask a few questions. You mentioned that the positron case was different than electrons. So what was the, can you elaborate upon it? And
Yeah, so can you still see the screen?
yes.
Okay. So let's just look at this picture. So you have a laser pulse, and it creates the wake by blowing the plasma electrons out. Okay?
Yes.
And left behind is ions, unshielded ions, or what we call an ion column. So from Gauss's law, the electric field that the ions provide is radially outward, which then focuses electron beams. But if I put a positron beam in here, it's going to blow them out, not focus them. So unfortunately, when I use a positron driver, the plasma is not an antiplasma, where it's the ions which are blown out. So the point is that in these nonlinear wakes, accelerating positrons requires ideas where you back off and you don't make this wake so linear that the gap between here and here is thick enough that I could load a positron beam in here. We're also learning that if you use drivers, or if there's a way to create a small strip of electrons, plasma electrons back here, they can help guide the positron beam. So in a linear wake, there's complete analogies with how you would deal with electrons and positrons. So some people say, well, let's use that, or a hollow, there's another area people consider, which are hollow channels, on how to consider accelerating positrons. but they end up with their own issues. So accelerating positrons, or thinking about a way to get a strip of electrons down here, or novel ideas, is a wide open area of research at the moment. But that the main reason is in these nonlinear wakes, in which we have ideas for high energy transfer efficiency. So we have very well-defined beam loading scenarios that have efficiency. We propagated them and simulated them over meter distances. They will not work for positrons because they're in this nonlinear blowout regime. And although this is ideal for focusing electrons, that means they're really good at blowing positrons away.
Another thing you mentioned that you need, I didn't quite get it, you need asymmetric beams or something like that?
Oh yeah, so in a linear collider, not for a XFEL, but in a linear collider, at the end, you need to collide the electrons and the positrons. So if you took a round positron beam and a round electron beam, and you collided them together, then something called disruption occurs, which means that they are space charge neutralized, but their currents are not. So there are very large magnetic fields which cause the two beams to pinch rapidly. As they do, they radiate hard photons, and it's called beams, there's a name for it called beamstrahlen. And this, you lose energy, it causes events, and is something you want to avoid. So what they realized is if instead you used non-round beams, where the beams were narrow in one direction and wide in the other, this effect of the pinching or the disruption in the beamstrahlen is much, much better. So therefore, in all linear collider designs at the moment, the idea is that the particle beams, when they are collided, have an asymmetric spot size, which means they have asymmetric emittances. All right. Now, that means that when you're accelerating them inside of your stage, unless you figure out a way to take a round beam and then make the emittance bad, and not to say that you can't figure out a way to potentially do that, then chances are to make things simple, you want the beams to have different emittances in the two planes inside the plasma. But, maybe there's a way to work around that. But the main motivation, you have to go to the final focus, where you have to deal with the issue of beamstrahlen and disruption. And then that determines what we're left with when we're trying to accelerate the electrons and positrons in each stage. But that's the thought.
Thank you, Warren.
Okay.
Thank you for the lovely presentation. We'll talk to you tomorrow morning again.
Okay. Thank you.
Thanks a lot.
Okay.
Bye-bye.
All right. Bye.